Hello, and welcome to this short introduction to category theory. Think of this video animation, in fact, as an introduction to an introduction. We'll take little baby steps, and in a few minutes' time, hopefully you'll have an intuition for this elegant, beautiful subject that will allow you to explore the wonderful resources that are available on the internet with much more confidence, since most of them require some prior knowledge. From pure maths to computer programming, from the philosophy of mathematics to the foundations of theoretical physics, category theory continues to make essential contributions in expanding the boundary of what it is possible to understand. Category theory brings clarity to complexity. It helps us to see patterns that aren't visible initially, but do in fact exist at a deeper level. Imagine being in a thick forest surrounded by trees with huge trunks and rich foliage with leaves overhead that let in some light but only barely. Now imagine being lifted from the forest floor above the canopy to a point about 20 feet above the tops of the trees. Suddenly you can see the immediate surroundings. You can see how the forest is situated on the brow of a small hill, and that over there to your left, out in the horizon, there are some fields. Imagine now being lifted even further, to a height of 1,000 yards. From this distance a great deal more becomes clear. You can discern the topology of the land, the mountain range in the far distance beyond the fields that only a moment ago formed the limits of your horizon. Category theory provides us with the means to lift ourselves up from the thicket, to recognize deep patterns that would otherwise be hidden, and understand what those patterns might mean. Now that we've taken a couple of baby steps, let's go a little bit deeper. For linguistic and scientific purposes, we become used to defining things around us with labels and names. We do this to objects of all types. We put things into groups or sets. A chair, for example, is part of a group or a set called furniture, and the definite integral is a part of a group called calculus. Category theory reminds us that in fact the best and most effective way to understand things is not by their labels and names or the sets that they belong to, but instead by how they relate to each other. Let's start putting some core rules into place. A category is something that has objects and arrows between those objects. These arrows, sometimes called maps, or more formally, morphisms, have basic rules. For the purposes of this video, I'm going to refer to them as arrows. The most important rule is something mathematicians refer to as associativity. When an object in a category has an arrow to another object, which then has a further arrow to another object, then we can start to identify the arrows. Let's call the arrow from A to B as lowercase f, and let's call the arrow from B to C as lowercase g. Associativity just means that if we follow G after having completed F, then that's really just the same as going straight from A to C. Just as there are arrows between objects in categories, there are also arrows between categories themselves, and these, to distinguish them from arrows between objects within categories, are called functors. Functors are structure preserving. If we connect an object A from one category to an object, let's call it A prime, in another category, then a functor only works if the arrows that form the structure are preserved in both categories as a result of the mapping or the arrows. Finally, for now, there's a particularly powerful concept in category theory called a natural transformation. This is when two functors from one category, let's call it C, both map to another category, let's call this second category D, and then maps or arrows arise between these two functors themselves. Let's call the first functor small t, and let's call this second functor lowercase s. A natural transformation is simply an arrow from t to s. Rather magically, in the real world, a great example of a natural transformation is the determinant of a matrix in linear algebra. Determinants are an essential part of linear algebra and can be expressed as a value that reflects important characteristics of a matrix. Given how prevalent linear algebra is in so many aspects of our lives through artificial intelligence, understanding and using them is actually quite important. Whether it's a system running the smooth workings of an airport, or an artificial intelligence process that evaluates traffic at a busy website, linear algebra is an invisible part of our daily lives. Determinants are an example of natural transformations, and category theory helps us to generalize rules that in turn help us to design and construct complex programs. These are the basic concepts that underlie category theory, and these powerful ideas drive our mathematical understanding of the universe and the world around us. By the way, for those of you that are tempted to learn a bit more about linear algebra, there are some very good resources online, including a link that should appear on the screen about now. I hope that you've enjoyed this little excursion into category theory, and will be motivated to learn more and become confident enough to think about working through some of the many web resources now that you have an intuition for the topic.